At this point, we've seen how to solve systems of linear equations using graphing and looking for a point of intersection, and also using substitution. In this video, we're going to look at a third technique, which is sometimes called elimination, sometimes it's called addition. If I look at this system of linear equations and I imagine adding each of the terms straight up and down, notice that the y terms cancel out. When I add, these eliminate from the system. And so that's why this is sometimes called addition or elimination, because what we will be doing is we will be attempting to add the equations together, have a variable eliminate from the system, and it will help us to solve faster. So because I noticed that the 2y and the negative 2y will eventually combine to nothing, I'm just going to go ahead and copy these equations exactly as they are. In a future example, we'll see what to do if they do not immediately eliminate. But because the y's have the same number but opposite sign in front of them, we're going to go ahead and add these equations together. And when I add them, the 3x plus the negative 7x, that's going to give me negative 4x. The 2y minus 2y cancels or eliminates from the system. And then the negative 6 plus the 14 will give me 8. And I've reduced this now to a much easier linear equation. Negative 4x equals 8. To solve for x, I will remove the negative 4, which is currently attached with multiplication. So I will detach by dividing by negative 4 on both sides. This leaves me with x equals negative 2. Now, of course, that's not the solution to the system, because the solution should be the point, which has two coordinates, the point of intersection. So I need not only an x coordinate, but also a y coordinate. So to get that last part, what I will do is choose either one of the original equations to plug this x value into. I can pick either one. In this case, I might pick the top equation since the numbers are a little bit smaller. And in that equation, I will substitute this value of x for that variable. So where I saw the letter x from that original equation, I'm now going to replace it with its value, which we found to be negative 2. The rest I can copy paste. And now what I have is a linear equation where the only variable to solve for is now the y. So 3 times negative 2 gives me negative 6. And I have negative 6 plus 2y equals negative 6. I want to solve for y, so I need y by itself. Let's relocate this 6 by adding it to both sides. This leaves me with just the 2y on the left side. And then on the right, negative 6 plus 6 is 0. And then for my last step to isolate that y, I want to divide by 2. I'll do that on both sides to maintain the balance. And 0 divided by 2 is still 0. So now I have an x coordinate and a y coordinate. That will give me the solution to this system. Remember that the solution is the point where these two lines intersect. So my solution is negative 2, 0. So this is a really nice technique. It is going to help me avoid fractions in a lot of cases. Notice in this particular example, it would have been difficult to graph because I would have dealt with fractions. It would have been difficult to do substitution because every single variable has a coefficient in front. It would have resulted in fractions, but this was a nice clean way to get through the solution without having to deal with fractions. Let's take a look at a few other examples. So again, we're going to do another example of using the elimination, or sometimes called addition, technique. Again, we'll take these equations, the 4x minus 3y equals negative 5, and we'll take that negative 4x plus 5y equals 11, and we're going to add these equations straight down. This time, notice that the 4x minus 4x cancels away or eliminates itself from the system. When I combine the y's, I have negative 3y plus 5y giving me 2y. And then for the constants, negative 5 plus 11 will give me 6. And so again, by adding these equations together, eliminating one of the variables, we now have a much smaller and easier equation to solve for. So I will divide by 2 to isolate the y. We get y equals 3. But keep in mind, as we're solving these systems, there are 2 parts to our answer. These are going to be points of intersection, so we need an x-coordinate as well as a y-coordinate. I only have the y-coordinate here, so I have a little bit more work to do. What I will do is take that new piece of information and plug it into one of the originals. It never matters which one because we already used both equations at one point. I will go ahead and use the first equation here as the numbers are a little bit smaller, and maybe that will make my work a little easier. So since I know what the value of y is, I will replace the letter y with the number 3 that we found to be the solution for y down here. So where there's a y, let's replace that symbol with the number 3. Everything else will copy paste. And now we have an equation where only x is the variable to solve for. So let's clean this up. I'll take the minus 3 times 3 to say minus 9. And then as I work to get x by itself, I'll begin by relocating this 9. Since it's negative, I'll add 9 to both sides. And so now 4x is what I have on the left side. On the right, negative 5 plus 9 will give me 4. And now to isolate the x, we'll divide by 4 since that's attached by multiplication. And so now x equals 4 divided by 4, which is 1. And I now have an x-coordinate as well as the y-coordinate. So now I can write my solution as an ordered pair, x comma y. In this case, it will be 1 comma 3. So again, if I had graphed these lines on a coordinate plane, those lines would intersect at the point 1 comma 3. Let's take a look at an example where maybe there's a little bit more work to do at the beginning. This next example is going to be a little bit trickier. Let's just imagine if we added this equation straight up and down right off the bat, 3x plus 7x is 10x, so that x does not eliminate. And y plus negative 2y goes to negative y. That doesn't eliminate either. And so we have a problem because while this is called the addition technique, it's also called the elimination technique. Something should eliminate from the system when we add. And so the way these equations look right now, it's not helping. What we need to have is we need to have, for one variable or the other, we need the same number but opposite signs. That will cause them to cancel each other out. It looks to me like the easiest way to make that happen is in this first equation. If I multiplied that by 2, I would have positive 2y that combined with negative 2y would cancel out. So as long as I multiply both sides of the equation by 2, that'll be fair game. But let's manipulate that first equation in that way. 3x times 2 is 6x. Y times 2 is 2y. Negative 11 times 2 is negative 22. Now I'm going to leave the second equation exactly as it is. And just looking ahead, I can imagine that the 2y minus 2y will go away. So this is going to work now. Let's go ahead and set up our addition. 6x plus 7x is going to give me 13x. 2y minus 2y cancels or eliminates away. And then negative 22 minus 4 is going to give me negative 26. So again, just by manipulating that first equation ever so slightly, we've been able to add these equations together to eliminate one variable and make this a little bit easier to solve. So now to isolate x, I'm going to divide by 13 on both sides. And x will be negative 2. But as we've seen before, when we're solving these systems, there are 2 parts to our answer. There's the x-coordinate and the y-coordinate. So let's go back and plug this x value into one of the original equations. I'm going to go ahead and pick the first original, which was 3x plus y equals negative 11. Always go back to the very original. Don't go back to one that you had manipulated. So go back to the original, but where I saw the letter x, I'm going to write what it actually equals. So instead of the letter x, we're going to replace that with the number -2. Everything else I can copy. And now it's a matter of solving for y. So I have 3 times -2, which is -6. I want y by itself, so I'm going to relocate that 6. Since it's negative, I'll add to both sides. And so now y is by itself on the left. On the right, -11 plus 6 gives me -5. So I now have a value for x as well as a value for y. And I can write my solution as an ordered pair with x first and y second. So x will be -2, comma, y is -5. And again, what this means is if I graph these two lines on a coordinate plane, they would intersect at the point -2, comma, -5. Let's take a look at another one where we have to manipulate one of the equations before we add them. So again, we have an example where if I tried adding immediately without doing anything else, nothing would actually eliminate. Currently, 10x plus -5x is just 5x. That doesn't go away. 3y plus -4y is -y, which doesn't go away. So that's not good enough. So we look at these two equations and ask, what's the easiest way for us to make for one of the letters the coefficients be the same number but opposite signs? It looks to me that the easiest fix would be to take this bottom equation and multiply it by 2. If I multiplied -5x by 2, that would give me -10x. 10x with -10x will go away. So let's try that. I'm not going to touch the first equation. That first equation is just going to be copied. But now the second equation, I'll multiply everybody by 2. So -5x times 2 is -10x. -4y times 2 is -8y. And on the right side, 16 times 2 is 32. So just make sure if you are going to manipulate an equation, make sure you do the same thing to both sides. It's again maintaining that balance. So I multiplied everything by 2. And now I'll combine, I'll add these equations. 10x plus -10x eliminates itself from the system, so that's gone. 3y plus -8y is -5y. And on the right side, -12 plus 32 gives me 20. And so again, what we've done with this elimination and addition technique, we have created a smaller equation with just one variable that we can now solve for pretty quickly. To isolate the y, we'll divide by -5. And so we get y equals -4. Again, that's only half the battle. We need 2 parts to our solution. There's an x-coordinate and the y-coordinate. So I'm going to plug this back into one of the originals. I'll go ahead and do the first original. It has fewer negatives. It doesn't actually matter which original equation you choose. Just make sure it's one of the 2 originals. And so now wherever I see that y, I'm going to replace that symbol y with -4. So where there was this y, I will put -4 instead and copy everything else. So I'm just plugging it in, substituting it in. And so now I have an equation with just one letter. This time it's the variable x. So now I want to solve for x. So I have 10x, and then plus 3 times -4 is actually -12. And so now to solve for x, let's relocate the constant. Since it's negative, we will add 12 to both sides. Then I have 10x on the left. On the right, -12 plus 12 gives me 0. And then to isolate that x, we'll divide by its coefficient 10. And so we wind up with x equals 0 divided by 10 is still just 0. And so again, I have my x and my y coordinates, so I can write my solution as an ordered pair x comma y, in this case 0, comma, -4. So again, this is the point where those two lines intersect in a graph. So we've seen two examples where we can just add the equations as they were. We've now seen two examples where we had to manipulate one equation to make something eliminate from the system. Now let's take a look at a couple examples where it requires manipulation on both of the equations in order to get something to eliminate. So again, here we have an example where if I just start adding these equations, nothing's going to eliminate. 3x plus 2x is 5x, that's not gone. 5y plus -3y is 2y, and that's not gone. So I have to find some way to make one or the other variable have coefficients which are the same number but different signs. So as I look at this, neither of these have the same number, but the y's do have different signs. So the y's might be a good place to attempt an elimination. So what I want to do is I want to look at the coefficients 5 and -3 and ask, even though I do have already the opposite sign, what's a way that I could get these numbers to turn into the same number? You can think of it as a least common multiple. 5 can become 15 and so can 3. That's one way to look at it. So what if I multiplied this entire first equation by 3 and this entire second equation by 5. That would turn 5y into 15y. It would turn -3y into -15y, and then they'll cancel. So let's give this a try. Make sure that you're multiplying everything in that equation by the same number so it maintains that balance. So 3x times 3 is 9x. 5y times 3 is 15y. And on the right side, 2 times 3 is 6. For the second equation, 2x times 5 is 10x. -3y times 5 is -15y. And 14 times 5 is 70. So just double check the way we've multiplied by 3 and by 5, we now have y's eliminating. 15y and -15y will cancel. So this is what we want to see here. So I add everything up. 9x plus 10x gives me 19x. The 15y's cancel. And 6 plus 70 gives me 76. So now to isolate the x, I want to divide both sides by that 19. So I get x equals, and then 76 divided by 19 should be 4. But again, we're not done because each solution to a system needs an x value and a y value for that ordered pair. We now have the x value, but we still need the y. So we're going to plug it back into one of our originals. I'll go ahead and go with the first original. The numbers are a little smaller. So 3x plus 5y equals 2. Where I had the letter x, I will now write 4. So where I had x here originally, I will replace that with the number 4. So I've got 3 times 4, and then I'll copy the rest. And now this is an equation where only y is the variable to solve for. So let's clean this up. 3 times 4 is 12. And if I'm trying to get the y by itself, let's relocate that number to the other side. So let's take this positive 12 and we will relocate it with subtraction. That will give us 5y on the left. And on the right, 2 minus 12 gives me -10. So now for my last step to isolate that y, since there is a 5 attached with multiplication, let us detach it with division. And it's fine as long as we do it to both sides. So now I have y isolated on the left. On the right, I have -10 divided by 5, which is -2. And now I've got both my x and y coordinates. So I can write my solution as an ordered pair, x comma y, which in this case is 4, comma, -2. So this one was tougher because we couldn't use what we originally had, and we couldn't just manipulate one equation. We actually had to manipulate 2 to get the coefficients to essentially match, but with different signs. So let's look at one more example to see if we can do that again. So once more, I have an example where adding these equations as is will eliminate nothing. and it is going to require manipulation on both equations to be able to get the elimination to happen. So as I'm looking at my variables, there is really nothing that's jumping out to me as the right answer or the right way to do it. There are always going to be options for how you can do it, but what you want to be looking for is, can I make these numbers the same or these numbers the same and maintain that different sign? I might want to play with the y's just because the coefficients are smaller. If they're smaller, maybe they're easier to work with. They're not much smaller. I mean, it doesn't really make that much of a difference. But if I'm looking at the 4 and the 3, think about what they can both grow to become. Think of it as a least common multiple. I'm seeing 12 as the least common multiple. 4 can become 12, and so can 3. So let's try to make those coefficients turn into 12. To get 12 out of 4, I'd have to multiply by 3. And to get 12 out of 3, I would have to multiply by 4. Let's give that a try. So remember, if you're going to multiply by something for one term, it's got to be on every term to maintain the balance of the equation. So 7x times 3 gives us 21x. Negative 4y times 3 gives us negative 12y. And then 1 times 3 on the right gives us 3. For the second equation, same idea, this time multiplying by 4. Negative 4x times 4 is negative 16x. 3y times 4 is positive 12y. And on the right side, 3 times 4 gives us 12. Again, adding these straight down, 21x minus 16x gives us 5x. Negative 12y plus 12y eliminates or cancels from this system. And on the right side, 3 plus 12 gives me 15. So by manipulating these equations in this way, we've now added them to eliminate the y's, and now it's an easy equation with just an x. We will isolate that x by dividing by its coefficient 5. And we find that x equals 15 divided by 5, which is 3. Now our job is to take that x value and plug it into one of the originals. Let's do the second original. Negative 4x plus 3y equals 3. It doesn't actually matter which equation you plug this into because we technically already used both equations. So this is just me just randomly picking the second one. But where I see the letter x in my original equation, I will now replace that x with the number 3, which is its value. So instead of x, I have 3. Everything else will stay the same. So now to solve this equation for the only variable that I see, y, let's clean things up. Negative 4 times 3 is negative 12. And if I want to get y by itself, I do need to relocate the constant to the other side. Since it's a negative 12, I'll add 12 to both sides. So now 3y is on the left, and on the right, I have 3 plus 12, which is 15. So now my last step is isolating the y by dividing by 3, and I get y equals 5. So now I have my x value and my y value, both coordinates that I need for my solution. Remember that when we're solving a system, we're asking what's the point where these two lines intersect. And so in this example, they intersect at the point 3, 5. So we've seen several examples. Let's take a look at 2 more where we have those special cases where we have the inconsistent system, which has parallel lines that never intersect, and we'll also look at a dependent system where the lines are actually the same and they intersect everywhere on that line. So again, in our first step, we want to try and find a way to make it so that for one of our letters or the other, the coefficient winds up being the same number but with different signs. Let's try working on the x's because those coefficients are quite smaller. They might be easier to think about. If I wanted to turn 2 and 5 both into the same number, their least common multiple would be 10. So to get 10 from 2, I'm going to multiply by 5. And to get 10 from 5, I'm going to multiply by 2. So let's do the multiplication. Remember, we have to hit every term on both sides to maintain the balance. Let's see what happens here. 2x times 5 gives me 10x. Negative 8y times 5 gives me negative 40y. And on the right side, 9 times 5 gives me 45. For the second equation, multiplying everything by 2, negative 5x times 2 gives me negative 10x, and that's what I was looking for. I was looking to try and eliminate those x's, but let's keep going. 20y times 2 gives me 40y, and on the right side, 6 times 2 gives me 12. So let's see what happens when I add. I do get those x's eliminating, which was the entire point of this manipulation. I was trying to get something to eliminate through the addition. But what also happened was the y's ended up eliminating. And so everything has canceled from the left side of the equation, leaving me with 0 on the left. Just nothing is over there anymore. But on the right, 45 plus 12 gives me 57. So if I told you that 0 is the same thing as 57, you'd say, no, it's not. That's not true. That's a false statement. So this here is a false statement. This is not helping me solve for x or y because x and y have both gone away. They've both eliminated. If they're disappearing, it means their value doesn't matter at all. If they disappear, they don't matter. This is going to be a false statement, which we call a contradiction. And if we reach a contradiction, no matter what x and y were, then there is no possible truth to this. This is always false. There is no truth. That means there is no solution. And if there is no solution for a system, that means we must have parallel lines that never intersect. There's no intersection point. We call this an inconsistent system. So again, an inconsistent system is one with parallel lines that never intersect, so there's no solution. And that happens because x and y eliminated both of them. And so that means it makes no difference what x and y are, you will always wind up false. You will always wind up with no truth, so no solution is possible. We've got one more, and I bet you can guess what kind it's going to be. So again, as we look for a way to add these equations and make something eliminate, I would focus my attention on the coefficients, which are smallest. They tend to be easier to think about. So if I want the coefficients on x to become the same, right now they're different numbers, they are different signs, which is good, but can I make those numbers become the same? What's the least common multiple of 2 and 3? It should be 6. 2 can become 6 if I multiply it by 3. 3 can become 6 if I multiply it by 2. And again, when we multiply and to manipulate these equations, we have to multiply every term on both sides to maintain that balance. So let's see what this gives us. Negative 2x times 3 gives us negative 6x. Positive 10y times 3 gives us positive 30y. And on the right side, negative 2 times 3 gives us negative 6. For the second equation, we'll do the same thing, but this time times 2. 3x times 2 is 6x, and we can see that the x's will be eliminating, which was our goal. But we also see negative 15y times 2 giving us negative 30y, which is interesting. Then we also, on the right side, have 3 times 2 giving us 6. So when I go to add these equations now, the x's eliminate, the y's eliminate, and so the left side is just 0. There's nothing there. On the right side, negative 6 plus 6 is also 0. So we now have 0 equals 0, which if I told you 0 is the same thing as 0, you'd say, yeah. So that's not telling me anything new. That's a true statement. It's true all the time. But it's not really telling me anything interesting, anything I didn't already know. This true statement we call an identity. And what this is saying is because x disappears and y disappears, their values don't matter. No matter what x is and no matter what y is, we will always have truth somewhere. We will always have truth. This is a situation where we have infinitely many solutions. And so visually, unlike the parallel lines which never touch, this is an example of where the lines are actually the exact same line and they touch everywhere on the line. So there are infinitely many points on the line. That's where these infinitely many solutions are. This is what we would call a dependent system. So when you work with these special cases of inconsistent and dependent systems, basically what happens is you start the process like normal, but you eventually hit a dead end where you can't solve for X and you can't solve for Y because they've gone away and you can't get them back. So you hit a dead end, and then based on whether that statement's true or not, you make a conclusion of whether you have infinitely many or no solutions. So keep in mind that this is all about systems of lines. So you're seeing how lines are either parallel or they intersect at one point or they are the same line. And that's what our solutions are representing, is the point of intersection. If there doesn't exist one, it's no solution. If there's one point of intersection, it's just one ordered pair. And in this case, where we had the same exact line, we end up with infinitely many solutions.